This is Euclid Book 10, proposition number 59. And do not turn off this video after I finish this proof. The reason for that is because we have yet another lemma. Not a lemon, a lemma. Okay. Alright, this one says, if an area be contained by the rational straight line and the sixth binomial, the side of the area is the irrational straight line called the side of the sum of the two medial areas. For let the area A, B, C, D, this one right here, this whole great big thing right here, be contained by the rational straight line AB, that's this one right here, and the sixth binomial AD, which is this one right here, divided into its terms at E, which is right here, so that AE is the greater term. This is going to be bigger than this. I say that the side of AC is the side of the sum of two medial areas. Let the same construction be made as before shown. We've been using this now for several proofs, and this will be the last one. Thank heavens. It is then manifest that MO is the side of AC. Okay, so this is going to be this. And then MN is incommensurable and square with NO. So these are incommensurable. Now since EA is incommensurable in length with AB, okay, EA, which is right here, is incommensurable with this. Therefore EA and AB are rational straight lines commensurable in square only. So the only time that this line here is commensurable with this is if you square them both. Okay? So this is commensurable with this, but this line is not commensurable with that. Therefore, AK, that is the sum of the squares on MN and NO, okay, so this whole area right here, this and this combined, is the sum of this area and this area. That whole area right here is medial. That's by Euclid Book 10, proposition number 21. Again, since ED is incommensurable in length with AB, okay, this is incommensurable with this. Therefore, EF is also incommensurable with EK. This is incommensurable with that. That's by Euclid Book 10, proposition number 13. Therefore, EF and EK. Here's EF, here's EK. They're rational straight lines commensurable only in squares. So if you square this and you square that, they're commensurable. Otherwise, they're not. Therefore, EL, this area right here, which also happens to be the same area as this one. Okay? That is the rectangle MN and O. How is this the rectangle MN and NO? Well, obviously, two sides of this rectangle are going to be MN. This and this are the same length, so that's two sides of the rectangle. We already know that NO and NR are exactly the same length. So this is actually the length of NO. So that's how that rectangle is contained by NN and NO. Okay? Therefore, EL, that is MR, that is the rectangle MN and O, is medial. So this is medial, that's medial. And since AE is incommensurable with EF, okay, AE is incommensurable with this, AK is also incommensurable with EL. Okay. AK, which is this whole area right here, from here on over, that whole area there is incommensurable with this area right here. This is by Euclid Book 6, proposition number 1, and Euclid Book 10, proposition number 2. But AK, okay, AK right here, is the sum of the squares on MN and NO. If you add these two together, you get all of AK. and EL is the rectangle MNNO. Okay, so this and this are the same area. Therefore, the sum of the squares on MN and NO is incommensurable with the rectangle MN and NO. So, what that means is that if you add these two together, these two areas combined are incommensurable with this area right here. And each of them is medial. And MN and NO are incommensurable in square. Therefore, MO is the side of the sum of two medial areas, which is by Euclid Book 10, proposition number 41, and is the side of AC. Now then, what about this lemma? Okay. Well, now we have to turn the camera a little bit more towards my direction. And obviously we're going to have to tip this up just a little bit. Now you can see me. Well, sort of. Sorry about that. Alright. So here's the lemma. Let's go through this one, shall we? The lemma says as follows. If a straight line be cut into unequal parts, the squares on the unequal parts are greater than twice the rectangle contained by the unequal parts. Let AB be a straight line and let it be cut into unequal parts at C, and let AC be the greater. Okay. There's your straight line, and I bet you're going to need light for this. Hang on. That's better. Let's go on here. AB is the straight line. We're going to cut it unequally at C, and AC is going to be the greater part. Okay. I say that the squares on AC and CB are greater than twice the rectangle AC and CB. For let AB be bisected at D. Okay, so now D divides AB in half. So AD is going to actually be the same length as DB. So far, so good. Since then, a straight line has been cut into equal parts at D and into unequal parts at C, therefore the rectangle ACCB together with the square on CD is equal to the square on AD. So, we have to draw a rectangle. The rectangle is going to have two sides the length of AC. The other two sides are going to be the length of CB. Okay. There's that rectangle right here. Now we're going to draw that. Now we got to draw the square on CD. That's this line right here. We're going to turn this line into a square, and all four sides of that square are going to be the length of CD. Okay, and now we have to make one more square, which is this one right here. And all four sides of this square are going to be the length of AD. Alright, so this area plus this area gives you this. That's what he's saying. Okay. This is by Euclid Book 2, proposition number 5. So the rectangle AC and CB is less than the square on AD. Okay. This is less than this. I think you can figure that out by now. Therefore, twice the rectangle ACCB is less than double the square on AD. So if you multiply that area times 2, and you multiply that area times 2, this is less than this. That makes sense. Alright. But the squares on AC and CB are double the squares on AD and DC. Okay. So if we add these two together, they are double that of the area that you add with these. Okay, if we add these two areas together, if you add these two areas together, they're going to be about half of the size of adding these two areas together. Okay. This is by Euclid Book 2, proposition number 9. Therefore, the squares on AC and CB are greater than twice the rectangle AC and CB. Okay. And I just dropped my little dry erase board. Shouldn't have done that. Okay. So, if we add these two areas right here together, they are going to be greater than twice the area of this. And that's what that lemma is saying. Wow! That's a lot of stuff. Alright. I will tell you more in a future video. Stay tuned.